Well, it's Monday of week 3, and I just want to start off by talking about the midterm exam. I know it feels like we just started this class a couple of days ago, or a couple of weeks ago, and it's true, we did. But it's already we're almost halfway through the summer session. We got 6 weeks, and so we're going to have one at the end of week 3. So again, so today is Monday. We will have a review session on Wednesday. Okay, the review session is optional on Wednesday, and then we will have an exam on Friday. Okay, so it will be this Friday, August 21. Okay, and you can take the exam either at 10 a.m. to noon. The exam's 2 hours. Okay, and you can either take it at 10 a.m. to noon or from 8 p.m. to 10 p.m. Okay. You don't have to tell me which one you're going to attend. Just show up at your chosen time, okay? And hopefully by having 2 kind of time periods that will accommodate everyone around the world. I know some people are in different time zones where, you know, when we're meeting right now, it's like, you know, 2 in the morning or something. So hopefully by doing it at, you know, having 2 different times, 10 a.m. and 8 p.m., that's gonna accommodate everyone. So just keep in mind, this is California time, so wherever you are, please make sure you show up at the right time. Okay, we are going to proctor them via Zoom. Okay, so so you'll log in on Zoom, and you'll have your webcam on. But also you'll be muted, and if for whatever reason you don't want to use the webcam on your computer, you can also install Zoom on your phone, and then and you can use the you can log into Zoom on your phone. You know, the whole purpose behind logging in via Zoom is to kind of just make sure that students are by themselves and not working together. You know, sometimes, so that it's kind of just to discourage kind of any kind of dishonesty there. So, you know, so log into to Zoom with your cameras. The exams will be multiple choice and will be taken on CCLE. So you'll see a kind of a quiz thing show up on CCLE in the quizzes and exam section. Okay, the exam's open book, so you can use your lecture notes, you can use your textbook. You're allowed to use a calculator of any kind, and you can even use RStudio if you want to use that for calculations to calculate certain things. Okay, the only thing you're not allowed to do is to communicate with each other, so you can't be messaging at each other, you can't be talking to each other. That's the one thing that's forbidden. So so hopefully by proctoring via Zoom, that will discourage that. Okay, it's not Respondus, so it doesn't there's like it does not lock your computer or anything like that. It doesn't. I'm not going to be saving a recording or anything like that, but I do want you to be logged in, so I can at least see you and see that you're alone. So are there any questions regarding that? Okay, so we will have a review session on Wednesday. That will be the regular, kind of during our regular class time. There's no viewing quiz for Wednesday's session, so there's no, so attendance for the review session is optional. I'll go over exam content, do some example problems, and things like that. Okay. I'm sorry. So what's your question? So what about Wednesday's lecture? So, well, I don't know. Maybe this answers your question about Wednesday's lecture. There's another question. Will there be questions about RStudio on the exam? So there will not be any like coding questions or questions that are directly about R and RStudio, but there will be you know, there will be questions that you'll need a calculator to answer. And if, and in that case, if you want to, you can choose to use RStudio to kind of help you with your calculation, but it's not going to be required to use RStudio during the exam, if that makes sense. So you're not required to use RStudio to answer any of the questions, but using RStudio could be helpful for some questions, okay? But you can also answer those same questions with a calculator yourself. Okay, will we have a regular lecture in addition to the review session on Wednesday? No, Wednesday will be an entirely review session. Last quarter, the review session on Wednesday was a little bit short, maybe like an hour and a half rather than an hour and 50. You know, I worked through some questions, students had questions, and then and we wrapped up. So that was what Wednesday looked like last summer session. Okay, if you finish the meeting early, a midterm early, can we leave the Zoom meeting? Yes, yes. So that's what. Yeah, you don't have to stick around for the whole 2 hours. Is there no lab on Wednesday? No, there is a lab this week, okay? Lab 3 has been posted on CCLE, and your TAs will go over them probably today, maybe Wednesday. So you'll go over lab 3 at least on one of these days, and that will be that. I've also posted some practice problems on CCLE. Now, you do have to note here. Let me. Did I write anything about this? No, I didn't write anything about it. So the exam will be a mix of kind of calculation-based questions and kind of some conceptual / theoretic questions. So the exam, so there's going to be both types, conceptual questions and calculation questions. Okay, so I have practice problems of the calculation-based questions. Okay, so as far as the calculation questions go, I've got some practice problems here, and so they are on CCLE, and you can answer them, and the answers are also available. These are written in multiple choice form, which is how the exam is going to be written. But then the exam will also have kind of some definition / conceptual questions that will be multiple choice, and I don't really have practice problems for those. So just please keep that in mind, that there will be some definition / conceptual questions that will be on the exam as well. Okay, what's a good way to prepare for the conceptual questions? I don't know if I have exact tips other than review the notes. Yeah, I'm sorry. I would say review the notes. You know, pay attention to anything that's in bold print. Anything that looks like a definition there. So, okay. I normally hold office hours on Friday, but we're going to be having the exam at Friday at 10. So there's no office hours Friday at 10. But I will have office hours the day before on Thursday at 10 a.m. Okay, and just use the Zoom link for lecture to attend those office hours. Okay, any questions before I get started on today's lecture content? Okay, all right. Well, we'll go ahead and begin here. So, okay, so we left off last week in chapter 5 where we learned rules of probability, and today we will continue on the rules of probability and cover something called probability distributions, okay? And the reason why we bother studying probability is that what we want to do eventually is we want to be able to distinguish between actual phenomena and random coincidence, okay? And in order to understand what's the result of random coincidence, we have to learn probability, okay? So, you know, what is or isn't random, that's what we're doing at, right? And so kind of the an example question that we might be able to answer at some point is this question of, you know, is this carnival game that's been, is the carnival game a scam, okay? And so we say, you know, there's a carnival game that you spin a wheel, it's divided into 12 equally sized spaces, and then half of them are marked to be loser spaces, half of them are winner spaces with different prizes on them. And you know, after playing the game several times, your friend comes back and says, you know, I think the game is a scam because I played 10 times and I only won a prize 3 times, right? And if we think about it, you know, our friend is basically saying that, you know, if the game is fair and I played 10 times, I should be winning 5 times out of 10, okay? And the fact that he won only 3 times out of 10, which is less than 5, to him means that, you know, he's not winning as often as he should, so he feels like he's being scammed by the game, okay? And so the question that we have now is, well, does this mean it's a scam, or is it also possible that the game actually is fair, and just by kind of random chance or bad luck, you know, our friend had an unfortunate outcome where he only won 3 times out of 10 rather than 5 times, okay? And so today we'll learn how to calculate the probability of winning 3 times out of 10 playing a game, you know, where we basically should have a 50% chance of winning. And so this brings us to probability distribution. So on Wednesday of last week, we covered a bunch of rules of basic probability, and today we will expand on that and get into probability distributions. Okay, so a probability distribution describes probabilities, the probabilities that a random variable can take. Okay, so a random variable is a numeric outcome of a random trial, right? So you have some kind of random trial, such as flipping a coin, rolling a die, doing something, okay? But the key thing about a random variable is that the outcome of the random variable is recorded as a number, okay? The outcome is recorded as a number. In order for it to be a random variable, we can't just say, you know, if it's a categorical variable like whether the coin landed heads or tails, we can't leave it as heads or tails. It has to be converted in some way so it comes out as a number, okay? And what the probability distribution will show us is that, you know, if some of these numeric outcomes are more likely than others, the probability distribution will reflect that, okay? So it shows the probabilities associated with each of the possible outcomes. Okay, and we can represent them with a table or a graph, and I'll show you some examples here. Okay, so one random trial is that you know, we have a die and we roll it. Okay, so the die is, you know, a cube. Each side, there's 6 sides, and each side has equal probability. Okay, and the random variable can just be the number that shows up when you roll the die. Okay. So we don't have to do any conversions because the outcome is already a number, right? And so we could say random variable x, okay? Random variable x can take on the values 1, 2, 3, 4, 5, 6, and we've got a table, and it takes on the value 1 with probability 1/6, okay? And so what this here, the notation here is the probability that random variable x has this particular value x, okay? So the probability that the random variable x is equal to, say, 1, or the probability that random variable x is equal to 2 is equal to 1/6. So this is the probability of each outcome, and with a fair die, all 6 outcomes have the same probability of 1/6. If we wanted to create a graph to represent this distribution, it can look something like this, all right? We've got the different outcomes, 1, 2, 3, 4, 5, 6. And then the height of the bar represents the probability of each of those outcomes. And we can see that all 6 of these outcomes have the same height, okay? All 6 of these lines have the same height, which indicate that all 6 values have the same probability. Okay, so another example of a random variable is that we could say, let's flip a coin, okay? So the coin can land heads or can land tails. And we'll just, if the coin doesn't land heads or tails, we'll just ignore that outcome, right? If we flip the coin and then it rolls away, then, and we don't get to see how it lands, then we'll just ignore that outcome and flip another coin, okay? Or if it lands on its side, we will just not count that and we'll flip the coin again. So, so the coin can land heads or tails, but in order for it to be a random variable, we have to say the outcomes are numeric, okay? So what we'll do is we will convert the outcomes to a number. And so we'll say if the coin lands tails, then the random variable x will be 0. And if the coin lands heads, the random variable x will be 1, okay? So we can just say the random variable will be how many heads appear after one coin flip, okay? And so we can, if we kind of just shift our perspective a tiny bit, then we have a random variable, okay? So again, you're not allowed to just say the outcome is heads or tails. It has to be a number. And so in this case, we're going to say if it's tails, it's 0. If it's heads, it's 1. And the probability of getting 0 is 0.5. And the probability of getting 1 is 0.5, okay? And so this is our probability table here, okay? And then if we create a plot, okay, x can take on the value 0 with a probability of 0.5. X can take on the value 1 with a probability of 0.5, okay? And so we have basically 2 bars or 2 lines, one at 0, one at 1, and they're both the same height to indicate that they have the same probability. Okay. As we move forward, these things can get more and more complicated, right? So what if we flip a coin 2 times? Okay, so we're going to be flipping a coin twice, and the outcomes that can happen are the outcome goes heads, then heads, heads followed by tails. It can also go tails followed by heads, and tails followed by tails, okay? And so again, these are the possible outcomes of flipping a coin twice, okay? But again, in order for it to be a random variable, we have to think of a numeric outcome, okay? So we can't use the actual outcomes of heads, heads, or heads, tails as a random variable because those are not numbers. So what we can do, a suitable outcome that can be used as a random variable will be how many heads appear after 2 coin flips, right? How many heads appear, right? So we can say, you know, what could happen after 2 coin flips, you can either get 0 heads, 1 head, or 2 heads, okay? So 0 heads, the probability of getting 0 heads is 1/4. And so if we use the probability rules for the probability of a sequence of random events, sequence of independent events, then we can just multiply these probabilities. So if you get tails, tails, that means we got 0 heads. And the probability of tails, tails is the probability of tails multiplied by the probability of tails. So that's 0.5 times 0.5, or 0.25, or 1/4. So we get the probability of 0 is 1/4. Okay. We can also get exactly 1 head. okay, the probability of getting one head or after 2 coin flips is going to be 1/2. And that's those include the outcomes. Heads, tails means you saw heads once, and tails, heads means you saw heads once, okay? And so the probability of heads, tails is we do 0.5 times 0.5, and the probability of tails, heads is going to also be probability of tails times probability of heads, which is 0.5 times 0.5. And when you add those two together, you get 0.5, okay? And similarly, the probability of heads, heads is 0.25. And so there are 3 outcomes, and the probability of each of these is 1/4, 1/2 for getting 1 head, and 1/4 for getting 2 heads, okay? So the 3 outcomes don't have the same probabilities, but they're assigned this way: 1/4, 1/2, and 1/4. Okay, we have a question. It says, do we ever analyze the shape of probability distributions because it seems like we're assigning the variable numbers arbitrarily? So, so yes, we can analyze the shape of probability distributions. In our class, we're going to just focus on 2 simple probability distributions. We're going to look at the binomial distribution and the normal distribution, and we're not going to really discuss the shape, but certainly, you know, at a higher level class, the shape of the probability distribution becomes important. I would say at this intro level, you know, we've talked about the shape of regular distributions, and we will encounter probability distributions that, you know, are skewed or are symmetric and things of that nature. But we'll generally keep our discussion fairly simple here, okay? Are we assigning the number variables arbitrarily? You know, perhaps, you know, just as far as what's a heads and what's tails, you know, that can be arbitrary. You know, others of these things can be, like this, I think, is defined a little bit better. But yeah, you could equally pick something else as well, okay? What if there are multiple categorical variables? How do you convert that to numeric values? Okay, yeah, so this gets tricky, okay? So let's say we are talking about hair color, right? So you have, let's say you have blonde hair, brown hair, black hair, red hair, and things like that. You know, maybe some other quote unquote non-natural hair, right? Like somebody dyed their hair pink or purple or something like that. Yeah, how do we put these into numbers? Okay, it's not straightforward. What you don't want to do, okay, you do not want to just say, hey, this is going to take on the number 1, 2, 3, 4, and 5, okay? Because those things, there's not like a natural, well, okay, hair color, oh, I don't. All right, let's say states, okay? One could argue that there's an ordering of hair colors, but let's say there's states, right? Someone's from California, someone's from Texas, someone's from New York, someone's from Wyoming. How do we assign these to numbers, okay? So what you often have to do is you have to create one variable for each of the possible outcomes. And so you just have a variable for California, yes or no, and those will just be 0s and 1s. Texas, yes or no, 0s and 1s. New York, yes or no, 0s and 1s. And so generally, if someone is from, say, Texas, they'll get a 0 for California, a 1 for Texas, a 0 for New York, a 0 for Wyoming, a 0 for all the other 49 states, okay? But, you know, it gets cumbersome because now you have 50 variables, and each person is going to just have 1 1 and then 49 zeros, okay? So categorical variables are tricky to deal with because it often requires some kind of conversion there, or each category gets its own number or gets its own variable, and will be a 0 or 1. You know, and that's, again, assuming each person can only take on one variable at a time, so, or one categorical outcome at a time. The, you know, something like hair coloring could be what we say made ordinal, where maybe you go from light to dark shades. Okay, so you know, I guess the lightest color hair, like kind of like a platinum blonde, would be maybe gets a rating of a 1 or something, and then as you get darker and darker and darker shades of brown to black, maybe the numbers get higher, and then if somebody has, say, you know, something that doesn't kind of fit on this light yellow to brownish blackish spectrum, then maybe you have to have a separate variable for that that accommodates you know, other hair colors, right? Like you know, especially things like even like naturally occurring red hair, natural and things like that. You know, maybe you need to indicate some other value there. So it's complicated. As far as our class goes, we'll generally keep these fairly simple, and we're only really going to spend time looking at the binomial distribution and the normal distribution. But these are all very good questions discussing probability distribution, especially for categorical variables, which is a challenging thing even today for, you know, data scientists and stuff like that. So, okay. So anyway, going back to this, the outcomes of 2 coin flips, 0, 1, or 2. Okay, the probabilities are 1/4, 1/2, and 1/4. And if we represent it graphically, it looks like this. Okay, so 0 has a probability of 0.25, 1 has a probability of 0.5, and 2 has a probability of 0.25. All right, here is, maybe we can talk about that carnival game. And a carnival game involves spinning a wheel into 12 equally spaced sizes, okay? And 6 of the spaces are marked lose or loser prizes. 5 of them are marked you win a small prize, and 1 is labeled you win a big prize, right? So you can imagine you got these this wheel, 12 spaces, and you know, half of them are lose, half of them are winners, but we also have the small prize versus the big prize, okay? So how do we turn this lose, small prize, and big prize into a numeric outcome? Okay, so these are, you know, different options exist, but one that we might be able to use will be the dollar value of the outcome, right? So we could say the loser prize has a dollar value of $0, okay, whereas the small prize has a dollar value of $1.50 or $1.50. And the big prize has a dollar value of $6, okay? So we might choose values such as this, and then our probability table, our probability distribution looks like this, okay? 0 takes on, we can get the value 0 with probability 1/2, or 6 out of 12. We get $1.50 with probability 5/12, because 5 out of the 12 spaces are small prize. And then the big prize of $6 we get with probability 1/12, okay? And if we create this plot, this is what the thing might look like, okay? 0 has probability of 1/2. 1.5 right here has the value probability of 5/12, which I think is like 0.4183 or something like that. And then the probability of getting 6 is 1/12, which is you know, 0.083. So so that's this this height over here. Okay, and so this will be the outcome of this probability distribution. Okay. So all of the examples we've seen so far are what we call discrete random variables. Okay, a discrete random variable means you are able to write a list of the different outcomes in a table, okay? So for the prizes, we're able to say there are 3 different outcomes. You can get $0, $1.50 prize, or a $6 prize. there's really only a few possible outcomes, so we're able to list them off on a table. When we roll the die, we can list off. You can get the number 1, 2, 3, 4, 5, or 6, okay? Those are discrete outcomes because we can write them down and we can write all of them, okay? If the random variable can take on decimal values and you cannot list all of the outcomes, then the random variable is continuous. You know, for example, if I say we can get a number between 0 and 1, okay, and any number between 0 and 1 is possible, then you cannot list off all the possible outcomes because, you know, how many values are between 0 and 1? Well, there's infinitely many. There's infinitely many, right? You see, because you can get 0.1, you can get 0.001, 0.00012, 0.0001001, you know, and it's not going to be possible to make a table with every single possible outcome. That table would be infinitely long because there are infinitely many values between 0 and 1, okay? And so, so if you have a situation like that, that's known as a continuous variable, a continuous random variable. And so a continuous random variable cannot be represented with a table of probabilities, okay? And instead, what we have to do is we have to represent a continuous random variable with a line or a graph, okay? You can also represent them with a mathematical equation, which we'll call a density equation. But you know, in our class, we're only going to look at the graphs. We're not going to deal with the mathematical equations. There are some really interesting things that happen with these mathematical equations that, you know, again, if you're interested, I can't help but promote the stats major and say, you know, take your theoretic math statistics class, because there's neat things to learn about the mathematical equations, but we won't worry about that in our class. We're just going to represent them with a graph, okay? So, so here's just an example of, you know, one that's discrete and one that's continuous, right? So one is we can say, let's select a random person, and the variable we're going to record is how many siblings does this person have, right? And as far as this goes, we're able to list the possible values, okay? So a person can have 0 siblings, a person can have 1 sibling, 2 siblings, 3, 4, all the way up to some arbitrarily large value. I think the world record for number of births given by a single mother, I think, is 69 children or something. I think that was some mother in Russia where she had this thing where she every time she got pregnant, not every time, but like almost every time she got pregnant, it was multiple births. She gave births to triplets multiple times. I think she had this unique thing where there were just many ova being released, and so anyway, 69 children, which is crazy to think about, but but anyway, you can still list them off. You can list off 0 up through 68 siblings or something, but it's possible to list off all the outcomes, okay? And so this would be a discrete random variable because we are able to list off the outcomes. Sorry, so let me tend to my dog for a second. All right, he's fine. He's fine. Okay. All right. On the other hand, we have we can also select a random person, and what we can do is we can measure the person's height in centimeters or inches, or you know, any type of measurement that we take in terms of length or weight or whatever it might be. That would be a continuous random variable because, you know, as far as somebody's height goes, that person could be 180.0 centimeters. If you have a very accurate measuring device, maybe they're 180.01 or 180.0127, and it can be, you can have a bunch of decimals if you have a very precise measuring thing, and so because there's infinitely many values that are possible for someone's height, and we're limited only by the precision of our measurement, this is a continuous variable, okay? Because we can take on all of these different values here. All right, so I hope that kind of clarifies some of the differences between discrete and continuous. Okay, what about age? So a lot of these questions, or a lot of the whether a variable is discrete or continuous depends on how you record, right? So if you think about time, so age is really is a measure of time, right? Like how long have you been alive? How many revolutions around the sun have you completed? And if you think about time, time is actually a continuous variable, right? Perhaps you've been alive for 21.644787 years, okay, whatever, right? If we were able to measure the exact, if we knew the exact time and date and time of your birth, we could calculate exactly how many minutes or how many years have passed since then. But most people, when you ask, what is your age, they report a whole number. They report a whole number. I'm 22 years old. I'm 18 years old. I'm 47 years old. They report just a whole number. And if you're only going to record a whole number, then it's going to be discrete. Okay. So, so it depends on how the variable is being recorded. That's going to determine whether it is discrete or continuous. Okay. All right. Another example of a continuous random variable is, say, waiting time. Okay. And so let's say there's a bus, a very reliable bus that comes every 12 minutes. Okay. And a person arrives at the bus stop at a random time. Okay. And so what we can do is we can say the random variable will be how long the person waits until the next bus. Okay. And this random variable can be any value between 0 and 12, right? And it can have values. It can have decimals, and all values between 0 and 12 have an equal probability, right? So the person can get to the bus stop just as the bus is about to leave, but is able to get on, right? So the person arrives, gets on, and immediately the bus takes off. So they have a wait time of 0, okay? On the other hand, you can have someone that comes 1 second later and whatever, maybe it's a robot bus driver that, has no sympathy for the person who arrived 1 second late. And so this person arrives and says, sorry, you missed the cutoff by 1 second, and the bus drives off, and now this person has to wait 12 minutes for the next bus to arrive, right? So the values between 0 and 12 have equal probability. And what we can do is we can represent this graph, this with a graph that looks like this, okay? And so we have between 0 and 12, we have equal probability. And then values outside, negative values will have probability 0, values higher than 12 will have probability 0. Okay, so this would be a probability distribution of bus wait times. And so this is a very important rule, okay? If the random variable is discrete, all the probabilities must add to 1, okay? You have that listing of probabilities. If you take them all, they must add up to 1, okay? All the probabilities themselves have to always also be positive, okay? On the other hand, if the random variable is continuous, then when you take the graph, okay, and you look at, say, the area underneath the probability line or the probability curve, the area underneath here, that area must always equal 1, okay? And the curve must always be positive or non-negative here, okay? So, so that's going to be the rule for probability distributions, is that they either have to add up to 1 if they're discrete, or they have to have an area of 1 if they're continuous. All right, so let's talk about the binomial distribution, okay? So the binomial distribution is a probability distribution for a special kind of random variable. And I'm gonna just kind of list all of these things off, and then we'll do some examples, which I think will help help make sense out of this, okay? So we can apply the binomial distribution in situations that meet all of these criteria, okay? So we're going to repeat the same random trial n times, okay? We repeat the same thing n times. Every trial must have two and only two outcomes. Either something happens or it doesn't, okay? Now, traditionally, these have been labeled success and failure, okay? But really, I think it should just be labeled like yes or no, something happens or it doesn't, okay? Because the thing that happens may or may not be a good thing, okay? And, you know, we generally associate success with good things and failures as bad things, but it could be something that is neither good nor bad, right? Like we could talk about, you know, I don't know, did something happen or not, or, you know, did we discover something or not, being neither good nor bad, but either it did or it didn't happen, okay? Every trial that we do, because we're repeating the same trial n times, every trial we do has to be independent of the other trials. So it's not like if you do something, it makes it more probable for it to happen again. No, we just have to say every single instance is independent, okay? And going along with that is that every time you do the trial, you should have the same probability of success P, okay? That this is not something that changes with time or changes with something else, okay? Every trial has to have the same probability, okay? And what we are going to record, the random variable x that we're recording, is the number of successes that we see after n trials. Okay? So here, some example that we can do is, let's say we have a coin, okay? And this is a special coin where when you flip it, it will land heads with probability 0.7, okay? Which means the probability that it doesn't land heads is going to be 1 minus 0.7 or 0.3, okay? So these are, this is the probabilities. And what we're going to do is we're going to flip the coin 4 times, okay? And the coin flips are independent of each other. And we're going to ask, what is the probability that we get heads exactly 1 time? Okay, what is the probability that we get heads exactly 1 time? Okay, so what I'm going to do is I'm first going to answer this question using the classical probability rules that we learned last week, okay? This is a binomial situation. It meets all of the criteria on this page. We're repeating the same trial n times. We're flipping a coin 4 times. Every trial has 2 outcomes. The coin either lands heads or it doesn't, okay? Each trial is independent of other trials. The coin flips are independent. And every trial we do has the same probability of success, which is 0.7 for heads. And what we're recording is getting 1 head, the number of successes, right? So what's the probability that we get heads exactly 1 time out of 4? Okay, so what we're going to do in order to answer this is I'm going to list the possible sequences where we get heads exactly 1 time in 4 flips, okay? And so these are there are only 4 possible ways to get this outcome of getting 1 head in 4 flips. You get heads, and then followed by tails, tails, tails. You can go tails, heads, tails, 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 heads, tails, and tails, 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 heads, okay? So those are the 4 ways in which you can get heads exactly 1 time out of 4, okay? And if you do follow the classical probability rules, you know, the probability of this outcome is going to be 0.7 for the heads, followed by 0.3 times 0.3 times 0.3, or 0.3 raised to the 3rd power, okay? And so we have 0.7 times 0.3 raised to the 3rd power, okay? If we do this sequence here, this probability is going to also be 0.7 times 0.3 to the 3rd power, okay? Because we've got tails, which is 0.3, heads, which is 0.7, tails 0.3, and tails 0.3. And, you know, multiplication, the order doesn't matter in multiplication, so we can kind of move things around. And we're also going to get this same probability of 0.7 times 0.3 raised to the 3rd. And so all 4 of these sequences will have the same probability of 0.7 times 0.3 to the 3rd. There are 4 possible arrangements, and each of these have the same probability. They're mutually exclusive. We don't have to worry about subtracting any kind of overlap or anything. And so the total probability is going to be 4 times 0.7 times 0.3 to the third. And we get this outcome of 0.0756. Okay, so let me just pause there and ask if the calculations on this page make sense to you guys. Give me a yes if you're good with that. Give me a no or throw in a question if you're not good with that. Okay, and then let me also give you your first quiz question for today. So week 3, Monday, your first quiz question is E as in elephant. E as in elephant is your first quiz question. Okay, so E as in elephant for your first quiz question today for week 3, Monday. Okay, and again, if anything's unclear as far as how I'm getting anything, you know, please don't be afraid to ask a question in the chat. Okay. All right, so this is the probability of getting this sequence, and all I've done is use the kind of the rules that we've done from classical probability, right? Okay. All right, what if we do the same question, same situation, except this time we're going to ask what's the probability we get heads exactly 2 times? Exactly 2 times out of 4 flips, okay? So here I'm going to list off the possible ways of getting 2 heads out of 4 flips, and you know they go heads, heads, tails, tails, and I've listed them all off, and there are 6 arrangements. Okay, there's no other arrangement for us to get 2 heads out of 4 flips. Okay, so if we limit ourselves to 4 flips, and we're going to say that you either get heads or tails, these are the only possible arrangements that we can do. Okay, and so if we do the calculations for any of these, the calculations for one of these sequences is going to be 0.7 squared, because we get heads twice, 0.7 times 0.7, and tails is 0.3 times 0.3, okay? So we're going to get 0.7 squared times 0.3 squared, all right? And again, we can rearrange any of these things so that we get the same probabilities. So all 6 of these sequences will have the same probability arrangement, and the total probability of all 6 arrangements will be 6 times 0.7 squared times 0.3 squared. So that's the total probability of all of these outcomes combined for a total probability of 0.2646. Okay. All right. So can we generalize this to some kind of rule, right? So when we looked at the probability of getting 1 head in 4 flips, what we had was each sequence had a total of 1 head and 3 tails, okay? Because we have to have a total of 4 flips, so which means if we have 1 success, there has to be 4 minus 1 or 3 failures, okay? And so the probability of one of those sequences, so if we go back to this slide, the probability of one of those sequences is the probability of success, 0.7, raised to the 1, number of successes, times the probability of a failure, 0.3, raised to the number of failures, okay, which is 3, okay? And so there were a total of 4 possible arrangements, so the total probability was 4 times that. And so if I just if I use words to represent all of this, I have the number of arrangements times the probability of success raised to the number of successes multiplied by the probability of failure raised to the number of failures. So this is what we have. Okay. Same idea applied when we were looking at 2 heads and 4 flips. Okay. If you have 4 flips and you get heads twice, that means you're going to get tails 2 times, right? Because you have to have a total of 4 flips. So you're going to get 2 heads and 2 tails for a total of 4 flips. And so the probability of each sequence is also probability of success raised to the number of successes, 0.7 to the 2nd power, multiplied by 0.3 to the 2nd power. Probability of a failure raised to the number of failures. Okay, and in this case, there were 6 possible arrangements. So the total probability is this, okay? So we take the probability of success, raise it to the number of successes, multiply by the probability of failure, raised to the number of failures, and then we have to multiply it by the number of arrangements. Okay, the number of arrangements. So how do we get to the number of arrangements, right? So what I did in these examples so far is I just listed them out. I just said, okay, we have 4 flips and we're going to get 1 head. Let's write them out. There were 4 arrangements. I said 4 heads and 4 flips and 2 heads. What are the arrangements? And we found 6 arrangements, okay? But you know, if I said we're going to flip the coin 10 times and I want 5 heads, listing off all of those arrangements is going to get quite tedious, and it's going to be very possible to miss one, okay? So there's actually a formula known as the binomial coefficient that can be used to find the number of arrangements, okay? And so, so this part right here, which is n choose k, this is how you write this. It looks like parentheses n over k, but it's n choose k can be calculated using this formula, n factorial times k factorial times n minus k factorial, okay? Now, if you're not familiar with factorials, you know, you don't have to worry about it, but it basically means you take the product of all the numbers less than or equal to n. So if you do 4 factorial, it's going to be 4 times 3 times 2 times 1, and you get 24. 5 factorial is 5 times 4 times 3 times 2 times 1, and you get 120 and things like that. So, but this is n choose k, and this represents how many sequences there are. So if you do 4 choose 2, you will get 6, which is what we had, right? So if we had 4 trials, and how many ways can we arrange 2 successes or 2 heads out of 4 trials? We have 4 choose 2. When you do the problem, you get 4 factorial, which is 24. 2 factorial is 2. And when you do this, you get 6, okay? If you did something like this with 10 trials and you want 4 successes, it's a lot more complicated. You have these really big numbers to contend with, okay? On my calculator, I have an NCR button. Here's my kind of on-screen calculator. Let me zoom in here. So what I can do is I can do 10, and then for me, over the division key, I can hit Shift Divide, and I get NCR for N choose R. So here I can do 10 choose 4, and that's equivalent to doing this 10 choose 4 business here. So I have 10 choose 4, and if I hit equals, I will get 210, okay? You can also do it on R. You can do choose, and you do 10 comma 4, and you get 210, okay? So this is, so I mean, you could do 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 factorial divided by 6 factorial, okay? And you get these numbers, and you get 210. But you know, this is a lot of work. Save yourself a little bit of stress by either using your calculator or R to get these numbers here, okay? And so to kind of, so this is what we've been discussing so far, and we've been saying number of arrangements multiplied by the probability of success raised to the number of successes, probability of failures raised to the number of failures, okay? We can replace all of these with symbols, and this is kind of the mathematical preferred way of presenting formulas, rather using symbols rather than words. But you know, if this the word version of the formula is preferable to you, that's fine. You don't have to use this, but this is how most textbooks will present this. And so the probability of getting X successes and N trials is going to be N choose X, okay, times P raised to the X, the probability of a success raised to X, the number of successes you want, multiplied by the probability of a failure, which is 1 minus P, raised to the number of failures. So if you have a total of N trials and you're going to have X successes, the number of failures you're going to have is N minus X. So, so that's what we have, okay? Now, so we can do this, and we can do n choose x, which is 6, 0.7 squared, which will be 0.49, times 0.3 squared, which is 0.09, and we multiply all those things together, and we get 0.2646, and that's fine, okay? You can also do this using, using R Studio, okay? And this is going to be, you use this formula, or this function dbinom, okay? And you plug in the values as in this order. You say how many successes you want, 2 successes, how many trials do we have? We have 4 trials, and each trial has the probability of success 0.7. And when you do this, it calculates it out and you get 0.2646, okay? You can also do dbinom. What's the probability of getting 1 success out of 4 flips if the probability of each flip has a probability of 0.7? And when we do this, we get 0.0756, which I believe matches what we calculated back here, okay? So 4 times 0.7 times 0.3 cubed is 0.0756. So that's the probability of getting 1 head out of 4 flips if each flip has a probability of 0.7, okay? So all of this lines up, okay? All right, so let's try an example here, okay? All right, so so in the 2019 season, okay, the Warriors were doing much better, okay, and Steph Curry, you know, probably one of the best basketball shooters in the league, possibly even one of the greatest of all times as far as shooting ability goes. He had a 92.6 free throw percentage, okay, which is very, very high if you don't follow basketball, okay. And so, you know, this may or may not be true, but let's treat these as if they were independent events, okay, saying every time he takes a shot, he's got a 92.6% probability of making it. And let's say he might take 5 free throws in a typical game, okay? So 5 free throws in a game. So we're gonna ask, what's the probability that he misses 1? Okay, what's the probability that he misses 1 free throw? All right, so how could we answer this, okay? Well, the probability that he misses exactly 1 free throw means that we're gonna have n equal to 5, okay? P is 0.926, that's the probability of success, and missing 1 means the number of times he makes it is going to be 4, okay? So missing 1 means he's made 4 of those baskets, 4 of those shots, and so we are going to do 5 choose 4, okay? 5 choose 4, 0.926 raised to the 4th power, and 1 minus 0.926, which is the probability of missing a basket. That's going to happen 1 time. So there's an overall probability of around 27%, 0.272, okay? And this can be done using R by typing in dbinom. What's the probability of getting 4 out of 5 times 0.926, okay? So question, okay, so we have a couple questions. Can we also do dbinom 1, 5, 1 minus 0.926? Yes, absolutely. So here, let me show you that those two are equivalent. So you could say dbinom, making 4 out of 5 with a probability of making it of 0.926 gives me this probability. I could also just say, well, what's the probability he misses 1, right? So we're going to say, what's the probability he misses 1, okay, out of 5? And the probability of missing is going to be 1 minus 0.926, okay? And if you do this calculation, you get the exact same value, right? So those things are the same, right? So yeah, could you also say that him missing the shot is the success, and instead do 5 choose 1? Yes, exactly. That's what we are doing right here. So we can say him missing the shot is the quote success. Like, right, if you are on the other team, you're playing the Warriors, okay, and you want him to miss, then the success, right, you're like cheering for him to miss, you can say, well, what's the probability he's going to miss 1? That's the success, and the probability of a success in this case is going to be 1 minus 0.926, right? So how would you put this into the calculator? I think this is how you would do this. If you want to do it on the calculator, you can do it this way. So you can do 5 choose, so we can do 5 choose 4 times, and we're going to do 0.926 raised to the 4th times point, I got to do 1 minus 0.926 raised to the 1. It's kind of redundant to write raised to the 1, but I'll go ahead and do it, and I hit enter, and I get the same number, 0.27204. And that's how we would do this. Okay, why is this equation different from the first factorial equation? I don't know if I understand this question. Why is this equation? This one? So this is the same equation that I presented earlier. Okay, so this thing is what we have right here. Okay, the factorial equation, maybe this is what you're talking about. This thing. This is equivalent just to this part, the n choose k part. The n choose k part, that factorial equation is only this part, the 5 choose 4. How do you figure out the number of arrangements? You would do the 5 factorial divided by 4 factorial times 1 factorial. But the full binomial formula will be this arrangement. Okay. So so anyway, Steph Curry is the Warriors were eliminated a long time ago from NBA contention. So and now we have NBA playoffs in August, which is I enjoy following basketball, so it's exciting for me. Yeah, we will see. We will see what happens. Yeah, I don't know if you guys followed. It was quite fun watching the Suns come out of nowhere, and then they still didn't make it, right? Who do I have? I'm biased, so my complete Los Angeles bias is rooting for and favoring the Lakers. They didn't look so great in the seeding games, but I like LeBron and I love the Lakers, so I gotta go for my home team. But the Clippers, the Bucks, who knows, right? Okay. Anyway, let's go back to our earlier problem with that carnival game of the wheel that we're spinning and all of that stuff. All right. And then after we do this, we'll take a break. Okay. Sorry, I've been talking this whole time. Okay. So, the story so far is the game, we should win half the time. Okay. Our friend played it 10 times and he only won a prize 3 times, right? So if the game's truly fair, we think, you should win something around 5 out of 10, but he only won 3 times, okay? So, so the question is, what's the probability that, if the game were fair, what's the probability that someone would win only 3 times or less, right? Our friend accused the game of being a scam because he only won 3 times, which would mean he would also accuse the game of being a scam if he won 2, 1, or 0 times, right? So we'll let's take a look, right? So what we have is we have a binomial problem where n is equal to 10. We're spinning the wheel 10 times. The probability of winning any one of those spins is 0.5. And we want to know, well, what's the probability that we get one of these outcomes where we win only 3 times, we win only 2 times, 1 time, or 0 times, okay? So we're going to need to find the binomial probability for when x is 3, for when x is 2, for when x is 1, and when x is 0, okay? And so to kind of just simplify this, I'm going to use r, and I'm going to do d binom 3, comma 10.5, plus d binom 2, blah, 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 d binom 1, plus d binom 0, okay? And when we do this, I get 0.1718, okay? We get around a 17% probability. So even if the game is fair, even if it was totally a fair game where, this carnival game is not rigged to, cause the player to lose more often, there's still around a 17% probability of ending up winning only 3 times out of 10. Okay, 3 times or 2 times, or three or fewer times out of 10. 17% probability, which is, it's not high, but it's also not that low. Like, it's not all that weird if this happens. Okay, like if somebody says, let's roll the die and let's see if I get a 6 and it happens to land on a 6, it's like a little bit impressive, but then it's also just, it could happen just by, random chance. Okay, let's skip this in favor of taking a break here. Okay, so let's go ahead and take a 5-minute break, and then we'll come back and we'll continue on deal with the normal distribution here. So we'll pause the recording. All right, a question came in, said, will the midterm cover this week's chapter, chapter 6? And the answer is yes. So I'm covering chapter 6 today. And yeah, today's stuff will be covered on the midterm exam. On Wednesday will be a review, so we'll go over whatever questions you have, and on Friday you'll have the exam, and that it will cover up to today's stuff. Okay, so yeah, exercises on your own time. You can try this out. It says admission rate at a university is 16%, which is I think something around. I think UCLA is something around there, and here are the answers. Okay. We can talk about the mean and standard deviation of a binomial distribution, which is just kind of, if you took all of the outcomes and you took the mean of them based on kind of their probabilities, then you would get this result. You would get the mean is equal to n times p, which makes sense, I think, right? So, if the probability of a coin landing heads is 50% and you flip the coin, say 100 times, how many times do you expect the coin to land heads? Well, you expect it 100 times 0.5, you expect it to land heads around 50 times out of 100. And so that's mu is equal to n times p, and so on and so forth. The standard deviation is sigma equal to square root of n times p times 1 minus p. And this is less intuitive, and I don't want to get into the explanation of this in our course. But here's just kind of this formula that will come in use, later on in the course. That's good to have. Okay. There's another question. It says, are the practice problems posted under week 3 a good representation of the difficulty of the midterm? Okay. So again, the midterm will be a mix of both definition/conceptual questions and calculation-based questions. And so the practice problems posted on CCLE, I would say, are a good representation of the calculation-based questions, okay? So it's easy to make practice problems of calculation-based questions. I think those are just because you can just kind of change up the numbers and still get some variety there. Whereas making good conceptual questions that are good practice, definition/conceptual questions that are good practice, that is still representative, it's kind of hard to do. So I don't have good example practice problems of those types. So my tip there would be to kind of just go review the lecture notes, and review anything that is bold print and any kind of statement that I seem to have emphasized in the lectures. So those we have. Okay. Another question, it says, will the midterm be the same format as the quizzes where we can do the, no, the midterm will be a different format. It is a online CCLE quiz. So on CCLE, it's gonna be just multiple choice, okay? So there's pros and cons to multiple choice. A pro is that, it grades quickly, and if you don't find your answer listed, then you made some kind of mistake along the way, and you can click it. Okay. The con is that there's no partial credit or anything, but this is what we'll have. So we're going to have a multiple choice exam on CCLE, and so it's going to be different from GradeScope. Okay. GradeScope is intended to be low stakes. Okay, so I know some of you maybe didn't perform as well as you would have liked on your Gradescope quiz, and that's okay. That happens. But they're meant to be low stakes. Each quiz is a total of 3 percentage points of your final grade. So even if you do like bad on a Gradescope quiz, like you get half the points wrong, right? So you only get a 50% on the Gradescope quiz. That's worth like 1.5 percentage points at the end of the day. So, or at the end of the course. So in my opinion, that's not a big deal. 1.5 percentage points to me, not a huge deal. I recognize it's different for you as the student. But I also just want to encourage you and not tie your identity to your academic performance. Okay, I know all of you got into UCLA because you had really good grades in high school or at your community college. You don't get into UCLA if you had bad grades generally. So I know pretty much all of you as students have been working hard to get good grades, but I think it's also a little unhealthy to attach so much of your identity and worth to your grades. And so don't see your performance on exam, don't let that to affect how you see yourself or anything. So but anyway, the Gradescope quizzes are intended to be low stakes, where even if you mess up, you can learn from it, and it will have minimal impact at the on your final course grade. Okay, so the other important thing we need to talk about is the normal distribution. This is going to be a very important distribution that we will encounter throughout the rest of the course, and so we'll cover it now. A lot of it centers around using a normal distribution table, which we will cover, so we'll go from there. Okay. So the normal distribution is a continuous distribution, okay? It's unimodal, it's symmetric, and it looks like this, okay? This is, when we talk about a bell-shaped curve, it's gonna look like this. Oh, another question. Have we given the second quiz answer? I have not. I guess I'll do that right now. Second quiz answer is E as in elephant. So again, E as in elephant is the second quiz answer. Okay, did we get that? E as an elephant for our second quiz answer. So, okay, unimodal and symmetric. Values near the center, near average, will show up frequently, okay? And then values that are greater than average show up less frequently, or less than average show up less frequently. And if you're far above average, so, average kind of being at the center here, if you're far above average, then it shows up much less frequently, or far below average is also much less frequently, okay? Like all probability distributions, and in this case being a continuous one, the total area, if you take the total area under the curve, this total area is equal to 1, okay? So this is the normal distribution. It occurs quite frequently in nature, okay? And there's something known as the standard normal distribution. The standard normal is the Z distribution, okay, which is actually what we have pictured here. The standard normal distribution is the normal distribution where the mean is equal to 0, the standard deviation is equal to 1, okay? Because it's a continuous distribution, the probability of getting any one exact value is 0. So the probability of getting 0 exactly, 0.00000 with infinitely many zeros following the 0 is the probability of getting any one exact value is 0. But, which is a little strange to think about, but because we can still talk about, 0 is still like the most probable value, in that like values near 0 are a lot more probable than values that are far away from 0, okay? But here we can just say, looking at this picture, what is the probability that I get a value? If this is the standard normal here, what's the probability that, if I pick a random value, what's the probability I get something less than 0? What is the probability that Z is less than 0, okay? And so the way we answer this is we are going to draw the picture, okay? And I'm going to draw a vertical line at 0, at z equal to 0. And then we're going to say, what's the probability that z is less than that? And that we can say, well, okay, well, we are covering, or talking about half of the picture, okay? Half of the picture is going to be 0.5. The total area is 1, and here we've got half of it less than 0. So the total area, that answer is going to be 0.5. The way we would express this with mathematical notation is we would write P that z is less than 0, and that's going to be equal to 0.5. Okay. All right, so this is what we have. Probability that z is less than 0 is equal to 0.5 because the total area is equal to 1. You know, what's the area that is less than 0? Half of it, okay? All right, so here's a question. What is the probability that z is greater than or equal to 0? And the answer there would also be, well, it's just the other side, okay? The other side is also going to be 0.5, right? So I can, you know, these two are technically complements. I could say the probability that z is greater than 0 is going to be 1 minus the probability that z is less than 0. And so we do 1 minus 0.5, and we get 0.5 here. All right, so that's just kind of the, yeah, can we do probability of z less than or equal to 0? Yeah, you know, so again, because the probability of getting any one exact value is 0, the probability that z is less than 0 and the probability that z is less than or equal to 0, those are both exactly the same at 0, okay? So I'll throw this in the chat here, but basically the probability that z is less than 0 is equal to 0.5, and the probability that z is less than or equal to 0 is also 0.5, okay? Both of the answers are 0.5 because the probability of getting z exactly at 0 is 0. So there's no chance of it landing exactly on the line, okay? It's a little strange to think about. The idea of values being infinitely close to each other is very strange. It's hard for our brains to comprehend because in everything in the universe, even down to atoms and the Planck length or whatever, you know, is maybe discrete. I don't know if continuous things actually exist in the universe. We can think of it, but they most likely exist only in kind of the math realm. If we talk about, I don't know if you remember the empirical rule from back in chapter 3. Back in chapter 3 was really only a week and a half ago. But so if you think back to, a week and a half ago, I think I said, approximately 68% of the data have z-scores between 1 and -1, okay? 95% of the data have z-scores between 2 and -2. You had a quiz question on this, so maybe you remember. Approximately 99.7% of the data have z-scores between 3 and -3. So we would write something like this. Probability that z is between 1 and -1 is around 0.68. Probability that z is between 2 and -2 is around 0.95. Probability that z is between 3 and -3 is around 0.997, okay? And whether these are less than or equal to's are, it doesn't matter because the answer is the same. And so here is kind of our picture. And so if I shade everything between 1 and -1, that covers around 68% or a little over 2/3 of the total area under the curve. If I go from 2 to -2, that's going to cover around 95%. And you can see if I go to 3 and -3, we're leaving just a tiny little sliver out here and a tiny little sliver out here. And that means we are covering 99.7%, okay? Almost the whole thing. Only these tiny slivers are less, and those make up, 0.003 or about 3/1000ths of the entire picture here. All right, so here's a question. Using the empirical rule, approximately what is the proportion that z is greater than 1? So if I shade everything to the right of 1, that is z is greater than 1, so z is 1, 2, 3, 1.1, everything greater than 1, what's the probability that I get z greater than 1? Just approximately using the empirical rule. So here we've got 68% between z is 1 and negative 1. Just kind of take a stab at this. Don't write down your answer in the chat just yet. I want you guys to take take half a minute here to think about it and say, okay, what is the probability that z is greater than 1 here? All right, go ahead. What do you guys think? If you want to, you can enter your answer in the chat. All right, so yeah, the answer is indeed something around 16%, okay? We've got about 68% between 1 and negative 1, okay? So we got 68% between 1 and negative 1, which means we have about 32% outside of that total. Half of that 32% is on the negative side, and the other half is going to be above 1, right? So half of 32 is below negative 1. The other half is above positive 1. So we're going to get something around 16% based on the empirical rule. Okay. What if we ask for something, though, that what proportion of z is less than 0.42? Okay, what's the probability that z is less than 0.42? Okay, so we can't use the empirical rule here, okay? If I draw a diagram, I've got 0 here, negative 1 here, negative 0.42, or I'm sorry, positive 0.42. 0 and 1 is here. Positive 0.42 is somewhere around here. What's the proportion less than that, right? So here's our picture, okay? I've got 0 in the middle. I'm going to put 0.42 here. And what's the probability of being less than 0.42? Okay, so just from the diagram, I know that whatever my answer is it's got to be greater than 0.5, okay? But in order to get a more precise answer, we have to use the z table. And so what we're going to do is we're going to break up 0.42 into tenths and hundreds. And the rows represent tenths and the columns represent hundreds, okay? So what you need to do is you need to go to CCLE. Under week 3, I have reference tables, okay? So what you'll want to do is you'll want to download these reference tables, and there's a whole bunch of these pages here, okay? There's the first 2 pages are the z table, the standard normal table, okay? And then there's technically a table of binomial probabilities, and then there's a t table for t distribution values. So this we will make use of this later on in the course, the t distribution table. But today we are going to just use the normal tables, okay? So so what I need to do is we are going to go look up z in the row. We want to find z is 0.42, and so to do that, I'm going to go to the row 0.4. Okay, z is 0.4, and I go to the column 0.02. So the intersection of z equal to 0.4 and the column 0.02, so 0.42 gives me 0.6628. So we go, so this is kind of what the table looks like. Keep in mind there are 2 pages to the z table. There's a negative side, okay? There's a negative side, and there's a positive side, okay? And so here my z is positive, so we're going to be on the positive side of the table. And what we do is we go to the row 0.4 and the column 0.02, and my answer is going to be 0.6628. Right? This can also be done using R. The function we use is p norm. P norm is equal to whatever the table gives us. So I can type in p norm 0.42, and R has a little bit more of a precise table, and it gives me 0.6627573. Okay, you know, our table says 0.6628, which is just basically this rounded off to 4 decimal places. Okay, Does the table show the area to the left or the right of the value? The table always, always, always shows the area to the left, okay? So both the z-table and p-norm, if you use p-norm on R, gives the area to the left of z, okay? If you want the area to the right of z, what you do is, well, you say, well, we know the total area is 1, so the area to the right is going to be 1 minus the area to the left, okay? So if you want the area to the right, you subtract the value from the table or p-norm from 1. So if we ask, what's the probability that z is greater than 0.42? Then the answer is 1 minus the area to the left. So we do 1 minus 0.6628, and we get 0.3372. Okay. Are there any questions on this? Does this make sense? All right, so what I want you guys to try is I want you to go and download this reference table. So log into CCLE, download the reference table, and I want you to answer these 3 questions. What's the probability that z is less than negative 1.4? What's the probability that z is less than negative 1.04? And what's the probability that z is greater than 1.04? Okay. So please take a minute or so to download this, download the table, and answer these questions. Okay. Keep in mind the table always gives you the area to the left. You can have both a negative and a positive side to the table. Okay, so I'll give you guys a moment to work on that. All right, how are you guys doing? Do you need another minute to get your answers? Are you guys ready for the answers? Are you just waiting for me to give you the answers? I don't know. Okay, you guys are ready? All right, so, well, you can look these up on in your Z table, okay? And so if we look up Z equal to negative 1.4, negative 1.4 is going to be this first column, negative 1.40, and I get 0.0808, okay? I could have done it using R, and I get 0.08075, which rounds off to 0.0808, okay? Negative 1.04, I take to the row negative 1.0, and I go to the column 0.04, okay? So I go to the column 0.04, negative 1.04 gives me 0.1492, 0.14917 if I use p-norm, okay? And then if I do positive 1.04, positive 1.04 gives me 0.8508 to the left, okay? But the question asks what's the probability of being greater than positive 1.04? So I'm going to do 1 minus 0.8502, okay? So when I'm sorry, 8508, right? So I do 1 minus 0.8508. And if I do that, I also get 0.1492, which was the answer to the previous question, okay? So 1 minus p-norm of positive 1.04 turns out to be the answer to the previous question, which was the area to the left of negative 1.04. So I get 0.1492 as well, okay? And so, you know, this reveals a little bit of a shortcut, and that is because the normal distribution is symmetric. The area to the right of z is equal to the area to the left of negative z. So the area to the right of positive 1.04 is equal to the area to the left of negative 1.04. Okay, so that's what we see. All right. This is useful when we generalize to any other normal distribution. So the standard normal distribution is centered at 0, has a mean 0, and standard deviation equal to 1. And what we can do is we can generalize this to other normal distributions or other data that follow a normal distribution. So we could say in the US, the height of adult men is approximately normal with a mean of 69.5 and a standard deviation of 3. So we can say the mean mu is 69.5 and sigma is 3. And we could say what proportion of adult men in the US are shorter than 72 inches, okay? So this is approximately what our diagram might look like. We have 69.5 in the center, and we're asking what's the probability of being at 72 or less. So we're asking what's the probability that height is less than 72, okay? So what we want to do is we want to convert everything to a z-score, okay? So we're going to say male height follows a normal distribution. This is kind of the shorthand way of saying this. Male height follows a normal distribution with mean 69.5, standard deviation equal to 3. And what we do is we're going to convert this to a z-score. So if you remember z-scores from a week and a half or so ago, we're going to do x minus the mean divided by the standard deviation. And we do 72 minus the mean of 69.5 divided by the standard deviation of 3. And so here I get a z-score of 0.83, where 0.83 standard deviations above the mean. And so what we're going to do is this question of what's the probability that height is less than 72 is equivalent to asking what's the probability that z is less than 0.83, okay? And to answer that, we go to our table and we go look up z equal to 0.8 in the column 03, 0.83. And the probability that z is less than 0.83 is 0.7967, 0.7967. Okay? And there's the, and that's your answer here. Okay? I think in the interest of time, I'm just going to kind of give you the answer for this. So what's the proportion? What proportion of adult men are shorter than 71 inches? Okay, if I just change this to 71 inches, then we convert to a z-score. We say x minus the mean divided by the standard deviation. 71 minus 69.5 divided by 3. I get a z-score of 0.5. And we ask what's the probability that z is less than 0.5. We go to our table and we go to 0.5, column 00, and we get 0.6915. And there's our answer. Okay, so it involves taking your thing, converting it to a z-score, and finding the area to the left or right, depending on the question. In our case, it says shorter than 71, so that's going to be the area to the left of 71. Okay. Another question could be, what is the probability that a randomly chosen adult has a height between 71 and 72 inches? Okay. And so for this problem, I actually have to kind of draw a little diagram for you guys. Sorry. Here, what we want is we want the area between 71 and 72 inches. Okay, so the area to the picture okay. Sorry. Okay. This is terrible picture here, but let's put 69.5 here, and I've got 72 and I've got 71 here. And what I want is I want the area in between. Okay, so the way I'm going to do this is this thing is going to be equal to, we're going to take the area to the left of 72, and we're going to do minus the area to the left of 71, right? So I've got 69.5, 69.5, but what, so if this is at 72, I'm going to do the area to the left of 72 and the area to the left of 71, and that will give me kind of the area in between. That's the idea here. I'm going to do this area minus this area, and what's going to be left behind, ideally, is going to be the area in between. No, ideally, that is what's, whoops, that's what's going to happen. Okay, so so we've actually already done the calculations for this. So the area to the left of 72 is 0.7967. So this is 0.7967. And then the area to the left of 71 is 0.6915. Okay, so whatever this is going to be the difference between 0.7967 minus 0.6915. So I'm going to get 0.1052. Okay, so around 10.5%. 0.1052. That's the area in between here and here. Okay, so that's how you would answer a question where it says, what's the probability that a height is between two numbers? Okay, and I guess I'll save this picture here into our week 3 slides. Okay. Okay. All right, and so our last set of questions now is going to be working backwards. Okay. So we're going to say, what size must a hat accommodate if it's to fit, let's say, 96% of people's heads, right? So when you buy a hat, there's like, it's adjustable, and you can there's like a max size that it can do, and like the smallest size it can do, and you probably want somewhere that it can do in between. And what we want is, let's say we want to be able to accommodate the middle 96% of head sizes, right? So there's always going to be someone maybe whose head is a little bit too big and it won't fit. Okay, and then maybe somebody's head is a little bit too small, and it's not going to be a good fit there either. So let's say we want the middle 96%, which means we want to go from the 2nd percentile to the 98th percentile. Okay, so and that will cover the middle 96%, right? And so what is let's say what is the size that corresponds to the 98th percentile, or what's the size that corresponds to, say, the 2nd percentile, or whatever it might be, right? So let's say the mean head circumference is 23 inches and the standard deviation is 0.8 inches. Okay, now I made those numbers up. Don't like fact check me. I don't know what the actual average head circumference is and what the standard deviation is. Okay, but it's probably something around there, right? Okay, so so let's just go with that, and say, and let's try to find what the 98th percentile is for head size, okay? So, so what we want to do for the 98th percentile, okay, is we want to go to our table and we want to find the z-score that corresponds to 98%, okay? And so when you look up 98%, I see two values, okay? So what we want is we don't want to look up, so this is what you do not want to do. You don't want to look up z equal to 0.98. Okay, z equal to 0.98 will give you this number. That number is not useful for us, okay? What we want to do is, because we're looking up the 98th percentile, we want to find the z-score that corresponds to an area of 0.98. Okay, we want to find what z-score will give me an area of 98%, okay? And we don't have an exact value. We have values that will be close. We have 2.05 and 2.06. And between these two numbers, the 2.05 is a little bit closer, okay? So yeah, this is the question. What is the z-score that gives 0.98 to the left, okay? So the number that corresponds to 0.98, the closest value is going to be 2.05, okay? 2.06 is also close, but 2.05 is closer, okay? So we have z equal to 2.05. We're going to plug that in and solve for x, okay? So our z-score formula is z equal to x minus mu divided by sigma. We have 2.05 is equal to x minus 23 divided by sigma 0.8. I multiply both sides by 0.8, and I get 2.05 times this is equal to x minus 23. I add 23 to both sides, and I get 23 plus 1.64 is equal to x, 24.64, okay? Because it's symmetric, this area that corresponds to the second percentile, 0.02, will be negative 2.05, okay? So if I want to find what is the z that gives me something close to 2%, 0.0202, that's going to be negative 2.05, okay? And you plug in and follow the same kind of answer here, okay? Just kind of on your own, you can look up the third percentile, and I've done the work here. Oh yes, third view quiz answer. Now that we're out of time for class, third view quiz answer today is A. A as in apple. A as in apple is the third view quiz answer for the day, and that's all we've got. Okay, third view quiz answer is A as in apple. Okay, that's all I've got for you guys for today. This covers chapter 6. You have some chapter 6 homework, so you can work through that. I've also posted practice problems on CCLE and try to work through those. And I'll have an optional review session on Wednesday. And if I don't see you there, I will see you guys on Friday for the midterm exam. All right. Have a good day, and we will see you guys maybe on Wednesday or Friday. Good luck as you study, and we'll see you then. Again, third view quiz answer for today is A as in apple. All right, thanks guys.